Okay, so it turns out there really wasn't that much left for us to do in this topic. So we're going to try to cover it pretty quickly. It'll just really just be a couple examples. I thought about showing the proof, but that would take a while. So what I do want to say is that the proof in here deals with what are called simple regions. And that is basically back when we first started learning about double integrals, we said there's type 1 and type 2 where you do dx, dy, or you do dy, dx. And a simple region is one you can do either way. Now, I wouldn't worry too much about that because I would say that they show a proof for simple regions and then show that a region that's not simple, like this for instance, that is not a simple region because you'd have two different, if you tried to go left to right, you'd have to keep switching between the different curves all along. But if you split it into pieces, you can split into a simple region or two simple regions. You could make more splits if you need to and just do one at a time. So really our theorem works for anything that is simply connected. So simple regions, I wouldn't even worry about that concept. I don't think it's that important. Simply connected, though, that is something you really need to understand. And that is, we said, anything without a hole in it. So the basic way of using Green's theorem is with simply connected regions, and that's what we did in class. I want to show a couple examples of how you can do ones that are not simply connected. So let's say we have this 2xy dx plus x squared plus 2x dy. And what we have is an ellipse that is given by x squared over 9 plus y squared over 4 equals 1. And then we cut out a unit circle from this. X squared plus y squared equals 1. And so the C will be both this and this, with the region here inside being that in between. Now this region is not simply connected. There's a big hole cut out the middle. So how can we do this? Well, the trick, the way I like to do this, is to open up a little gap. We can say, oh, that was more deleting than I intended, sorry. We can say, put what's got a little keyhole here. This is a fairly common trick when you're trying to do more complicated integrals. And just delete this part here, because now we have a single curve where we go around the outside, up here, around there, and back and around again. And we'll say the width of this is epsilon, and the width of this is epsilon. So the idea I want you to think of is it's almost a full ellipse with just a little opening here, because if we do that, then this region no longer has any holes in it. Okay, so let's see what this curve would be. Well, now that it's a simply connected region, we can just use Green's theorem. We can say this becomes double integral around r of the x derivative of this is 2x plus 2 minus the y derivative of this is 2x dA, which becomes 2 double integral of dA. Now, we just need to know what is the area of this thing, of this region we have here. And what we can do is we can get the area of the outer part minus the area of the circle inside. So let's say, what is the area of an ellipse with a little chunk taken out of it? So it'll be 2 times bracket. Okay, we saw in class the area of an ellipse is pi times this distance times this distance, the major axis and the minor axis, A and B. So it becomes pi times 3 times 2. Now that would be for the full ellipse, but we're missing these little pieces, this little epsilon piece. So the trick with this, whenever you are trying to take a wedge out of an ellipse or a circle, you multiply by the fraction of the ellipse you're doing. Actually, that might not be quite right, given that it's not a circle. Well, we would have to work out the area of this. Well, this is going to... Okay, so I'm just going to cheat a little here. I'm just calling this is like g of epsilon. It's some function of epsilon. It represents the piece of the area that we're cutting out here. Minus the area of the inside is pi times 1 squared. But the trick with this, what makes this work, is that we can now take the limit as epsilon goes to 0. So if we make this little wedge, the width of it, shrink down to 0, then it disappears. I guess this should be a 1 minus g of epsilon. I'm sorry, that would make more sense. Because if g of epsilon is the error we get for this, then as epsilon gets small, this vanishes. And what we're left with is 12 pi minus 2 pi, or 10 pi. Okay, now this idea of like creating a correction, a very small error, and then letting it shrink, that's key to calculus all over the place. We're constantly saying, get the best possible estimate, and then let the error shrink to make the estimate turn to the exact value. So that's the sort of thing you would do in an analysis class if you had a tricky integral. But we can have a shortcut here. See, the idea, what really happened, what made this work, is that if we went all the way around as a line integral, this piece going inward and this piece going outward, they're almost just going along the x-axis, but one is going to the left, one's going to the right. They cancel each other out. So the shortcut, proving it, is not something we're going to do. I'm just going to say it works like this. When we have a region with a hole in it, as we just did, is we can do the line integral along the outer part minus the line integral on the inner part. So I'm going to go in the clockwise direction here because I want it to be negative. Along both curves, if you're walking along it, the shaded part is on your left. But in this case, it is going in the counterclockwise direction, it's positive. Here it's the clockwise direction, go negative. So if I call this C1 and I call this C3, here there's a C2 and C4 that cancel out. So we can just say the overall integral for this whole region would be f dot dr C1 minus f dot dr C3. So yeah, it's as simple as do the outer one, do the inner one, and subtract. All right, so let's do one more. This one I really like because it shows up in a lot of other courses too. F of xy is negative yi plus xj over x squared plus y squared. And we want to show the integral of f dot dr along c is equal to 2 pi for any path with a positive orientation enclosing the origin. Copy that down if you need to, because it's going to have to move it off screen. And so that means P is negative y over x squared plus y squared. And Q is x over x squared plus y squared. As the denominator, x squared plus y squared gets distributed to both parts. Okay, so what we're saying is, let's say we got some weirdly shaped curve like this. We'll call it C1. Well, we can replace it with just a nice clean circle here, radius A, which we'll call C2. Now we know the integral on the whole curve, C is C1 union C2. So we're going to integrate along both curves. It'll have the effect of the outer one minus the inner one. All right, so how do we do this? Well, our formula says we can do the integral along C1 of P dx plus Q dy minus the integral along C2 of P dx plus Q dy. And that will equal the double integral across D of del Q del X minus del P over del Y dA. So if you look back at how P and Q were defined, that's just a Calc 1 problem. Well, no, there's X and Y, but it's a pretty straightforward partial derivative problem to get D of x squared plus y squared minus 2x squared over x squared plus y squared minus x squared plus y squared minus 2y squared over x squared plus y squared. There's an extra negative here, dA. And if you crunch this out, this gives me 0. The integral is 0. So what does that mean? Well, what it means is that we did C1, we got a number. We did C2, we got a number. But they add up to 0. And they subtract to 0, which must mean they are the exact same thing. Whatever we get for C2 has to be the same for C1, because when we subtract them, we get 0. So that means we can just do the integral along the circle instead of having to deal with a whole ugly squiggle like that. All right, so let's work that out. we have integral of f dot dr on C2. And just for the heck of it, let's just say a equals 1, because we just said no matter what size it is, it'll be the same thing, so why not just use the easiest circle of them all? So r of t is cosine t sine of t. R prime of t is negative sine t cosine t. So let's plug that in. We will get the integral from 0 to 2 pi of f of r of t dot r prime of t. dt. Well, that turns into, what is f of r of t? We can replace the x with r cosine of t. Or, I guess we can say cosine of t. If we're saying x is cosine and y is sine, then x squared plus y squared is just 1. So it just becomes negative sine t, comma, cosine of t. Just go back to where we defined what f was and plug in cosine for x, sine for y. Dot, negative sine t, cosine of t, dt. That, well, if you look at that, we get sine squared plus cosine squared. So that becomes integral from 0 to 2 pi of 1 dt, which is just 2 pi, which is what we wanted to prove in the first place. So why is that useful? Well, if you'll think about it, it's actually kind of surprising. There's a hole here. It's saying no matter what path we take around here, the integral of this particular field is always the same. And this shows up in complex analysis a lot. So, like I said, if you're taking complex analysis soon, which I would expect if you're an electrical engineering path, you probably will, I would suggest look over this example. Maybe not for this class. I don't think anything as bad as these is on the homework or the exams. But save this one, because it leads to what's called the Cauchy integral theorem. This is, so again, this is for future use. This is not for this class or formula. But it's really interesting when you have complex analysis how simple it can be, which is if you have some function where you put the part that causes it not to exist on the bottom. So in the last case, it would be z on the bottom. It just comes out to 2 pi I times plug into what's on top. And so it's a similar thing. This whole idea of we go one full circle around, and that's where the 2 pi comes from. And so you'd have a thing where you'd have like, do a whole integral around here. You would just say, well, here are all the different places where it doesn't exist, all spots in our domain, and you would just do an integral on each one individually and add them up. So anyway, that was just a couple extra things that I wanted to touch on. And like I said, this is probably not going to show up on the homework or test, but I want to show it to you just in case. All right, I will see you Monday. Have a good break.